This video is my attempt to prove the grid challenge that Mathologer discusses in his latest video. The link to his video is in the description, but I've summarized it as follows. You have 4 colors and a grid of 4x4 squares. You have to put the colors in the grid with the rule that each 2x2 square contains all 4 colors only once, including the middle 2x2 square, etc. Now, the challenge is to prove that all possible solutions to this problem would result in the corner squares having all 4 different colors without repetition. The following video is my attempt to prove this. I decided to use the numbers 1, 2, 3, 4 instead of the 4 colors, just for visual simplicity. Note that you can choose any 4 colors to correspond to these 4 numbers. The first observation I made is that there's a logical extension to the rule that each 2x2 square contains each number exactly once. The extension is that bordering squares must contain different numbers. To illustrate this, suppose this square contains a 1. None of these squares in gray can also contain a 1. Therefore, all of these squares in gray cannot be a 1. So, bordering squares must contain different numbers. You can actually also see this in the example that the Mathologer gives, where you see any given square has a different color than all the squares that are bordering it. This fact itself helped me to get a good start on this proof. The next decision I made was to start with the middle 4 squares. It doesn't matter how exactly we place the 4 numbers in these 4 squares, but obviously we can't repeat a number. So I chose to place them like this. If we look at the top left square, we see that it borders the 1, so it therefore cannot be a 1. Similar to how I solve Sudoku puzzles, we can place a 2, 3, 4 in that square to signify that all 3 of those possibilities currently exist. The top right corner can't be a 2, so let's put 1, 3, 4 there, and so forth for the other corners. For the 2 empty boxes at the top, they both border a 1 and a 2, so they both can only be a 3 or a 4. The same way, the 2 empty boxes on the left can only be a 2 or a 4. We can fill the other 4 boxes the same way. Now, we have all currently possible solutions captured here. However, to proceed, we need to branch into 2 options. If we look at the middle top 2 boxes, we could choose 3 and then 4, or a 4 and then a 3. So for branch 1, let's choose a 3 and then a 4. And at the bottom, we can choose a 1 and a 2. But if we choose a 3 in this box, then the top left corner can no longer be a 3. So only 2 and 4 are possible options there. The top right corner can no longer be a 4, so it can only be a 1 or a 3. The same with the bottom 2 corners. Now, we can see that the 4 left boxes have to be a 2 or a 4. The only restriction is that the middle 2 boxes have to be different. So we can choose 4242 or 2424. On the right, we can choose 1313 or 3131. I'll choose 4242 and 1313, but it really doesn't matter. That's it for branch 1. Fortunately, we have all 4 corners with different numbers, so that's a good thing. We've proven 1 branch. But what about the second branch? Well, actually, this is even easier because we can also eliminate the 4 as an option from the second box on the left since it borders the 4 at the top. We can do this for the other boxes as well. Now we just have to remove the 1 option for each corner that repeats with the number immediately above it or below it. When I redraw these numbers to line them up, we have our answer for the second branch. Again, fortunately, we have 4 different numbers in each corner. So 2 possible branches and both worked. That proves it, right? Well, unfortunately not so fast. Mathologer wanted us to prove that this works not only for 4x4 grids, but also for 8x8 and 12x12, or generally 4n×4n, or any multiple of 4. While this seems like a daunting task, what I realized is that we really only have 2 possible options for each 4x4 grid. So we just have to see what happens when we tile these 2 options together. Actually, we just have to see what happens to the borders when we tile them. So instead of branches, let's call them tile 1 and tile 2. With an 8x8 grid, let's place tile 1 at the top left. If we place another tile 1 to the right of it, it looks like the border still works perfectly well. If we place tile 1 to the bottom, again, it doesn't violate any of our rules. So let's do the same with tile 2. It looks like the borders don't violate any rules either. That means that however we place tile 1 with other tile 1s, they don't break any rules. And however we place tile 2 with other tile 2s, they don't break any rules. More importantly, the corners in both cases do maintain the requirement that they are 4 different numbers. The only other possible option here is to mix tile 1 with tile 2. So let's try that. When we do that, it looks like it starts to work, but not always as we proceed. So tile 1 and tile 2 don't play well with each other. That means to maintain the rules of the game, we have to only use all tile 1s or all tile 2s as many times as we want. And when we do that, we end up with 4 unique corners. That is my proof of the challenge from Mathologer. I'd love to hear your feedback. Do you agree with this proof, or did I miss anything? Put your thoughts in the comments below and check back for more math-related animations. Thank you for watching.